10,
CLS go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Every civilization, from the first humans who gazed up at the night sky to the physicists mapping distant galaxies today, has wrestled with the same impossible idea. How fast can we truly go? Not on foot, not by ship, not even by rocket, but across the cosmos, through the silent, endless darkness where distances are measured not in miles or kilometers, but in light years. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum. And let's ease into tonight's journey together. A light year. The distance light travels in a vacuum in a single year. Nearly 6 trillion miles. The fastest thing in the universe. The cosmic ruler of all interstellar journeys. To early humans, the stars were gods. To ancient explorers, they were fixed lights in a rotating dome. To modern scientists, they are worlds, suns and galaxies so far away that their light is older than entire civilizations. And yet, across thousands of years, one question has refused to fade. Is there a way to outrun the limitations of our world and cross these impossible distances? Because light does not crawl, it erupts. It slices through the vacuum at 299,792 kilometers per second, a speed so vast that even our most powerful rockets look motionless by comparison. Light is the messenger of the universe, carrying the stories of dying stars, ancient galaxies, and cosmic collisions across unimaginable expanses. And humanity wants to follow it. We want to travel not for days, not for years, but for light years, the true scale of the universe, to explore beyond the solar system, beyond our quiet arm of the Milky Way, beyond everything we know. But before we can even dream of interstellar voyages, we must confront a humbling truth. Humanity's fastest machines crawl through space compared to light. Where light races, we drift. Where photons sprint across galaxies, our spacecraft barely nudge past the boundary of our solar neighborhood. And still, we dream. We dream of ships that cut through space like light itself. We dream of crossing vast interstellar oceans in a single lifetime. We dream of touching the stars not as distant pinpricks in the sky, but as destinations. To understand what it means to travel light-year distances, you must first understand the scale of the universe, a scale so enormous, so indifferent to human measurement, that our familiar units collapse under its weight. Miles, kilometers, seconds, they crumble like dust in the wind. The cosmos forces us to speak a new language, a language of billions of years, trillions of miles, and distances so vast that light, the fastest thing ever known, requires entire lifetimes just to cross them. Humanity's earliest explorers thought crossing an ocean was an impossible distance. Then we realized Earth was a sphere. Then we reached the moon. Then we extended our reach into the solar system. Each time, our sense of distance expanded, but nothing could prepare us for the leap from planets to stars. Let's confront the truth. The nearest star to Earth, outside the Sun, is Proxima Centauri. It sits a mere 4.24 light-years away. 4 sounds small, but this is no ordinary 4. This is 4 times 6 trillion miles. 4 years of uninterrupted travel at the speed of light. 4 years in which photons, pure streaks of energy, blaze through the void without slowing. For us, traveling at our fastest speed, that distance becomes a staggering challenge. If the entire solar system were shrunk down to the size of a coin, the nearest star would still be several football fields away. That is how empty, how spread apart the galaxy truly is. And yet, this is only the beginning of the immensity. The Milky Way itself is 100,000 light-years wide. To cross it, even at light speed, would be like walking the Earth's circumference not once, not 100 times, but millions of times. You could live a full human life at the speed of light, and you would barely cross 1% of your galaxy. That is the scale you are dealing with. Distances so large they defy imagination. Distances so unfathomable that light itself, the universe's fastest traveler, takes centuries, millennia, and eons to cross them. But this is the truth that both humbles and inspires humanity. Despite the impossibility of these distances, we still look upward and imagine crossing them. Our tiny world orbits a modest star in a forgotten corner of the galaxy, and yet our curiosity burns brighter than suns. If we are to travel light-year distances, if we are to move from one star system to another, then our technology must evolve beyond rockets and chemical engines. We must rethink speed itself. We must challenge the very limits of physics, because light years are not just distances. They are barriers, tests, and dreams. To even begin the journey, we must first accept how brutally large the universe is and how small we are within it. And yet, being small has never stopped us before. Before we imagine slicing through space at unimaginable speeds, we must ask a sobering question. How fast can we travel right now? Not in theory, not in science fiction, but with real engines, real spacecraft, and real human technology. The truth is both humbling and inspiring. Humanity has already achieved incredible speed, but compared to light, we are barely moving. Let's begin with the fastest object humans have ever built, the Parker Solar Probe, a spacecraft launched by NASA to study the Sun. To survive the Sun's blazing gravity, it slingshots around our star again and again, accelerating faster and faster until it reaches a mind-bending velocity of 435,000 miles per hour, about 700,000 kilometers per hour. At that speed, you could circle Earth in under a minute. You could fly from New York to Tokyo in 45 seconds. You could outrun a bullet before it even leaves the barrel. And yet, even at this astonishing speed, reaching the nearest star would take more than 6,500 years. Why? Because in a universe measured in trillions of miles, even extraordinary speed becomes painfully small. Let's step back and look at our fastest achievements. Apollo astronauts traveled 25,000 km on their way to the Moon. Voyager 1, humanity's farthest traveling probe, moves at 38,000 km and has taken 47 years just to escape the solar system's edge. New Horizons, which gave us our first close-up images of Pluto, traveled at 36,000 km/h and still took 9.5 years to reach its target. And the Parker Solar Probe, our current record breaker, travels at just 0.064% the speed of light. Let that sink in. After thousands of years of technological progress, after mastering rocketry, orbital mechanics, and interplanetary travel, our fastest machine reaches less than 0.1% of light speed. It's like trying to swim across the Pacific Ocean by moving a few inches per hour. And yet, this tiny progress is monumental. Humanity's machines have left Earth. They have crossed the orbit of Mars, Jupiter, Neptune. They have touched the atmosphere of the Sun. They have left the solar system entirely. For a species that once believed the stars were unreachable gods, this is extraordinary. But the stars demand more. They demand speeds that dwarf anything we've ever achieved. They demand engines that outclass rockets, propulsion that rewrites our understanding of physics, and ambition powerful enough to overcome fear. Because if 0.064% of light speed takes 6,500 years to reach the nearest star, what would it take to cross even 1 light year, 10 light years, 100? From the moment humanity first discovered the astonishing speed of light, a strange kind of envy settled deep within us. An envy towards something that wasn't alive, didn't think, didn't dream, yet could do what we could not even imagine, cross the universe with ease. Light does not ask for permission. Light does not tire. Light does not accelerate slowly like a rocket fighting gravity. Light simply is, the ultimate traveler, the unquestioned champion of speed in our cosmos. But there is a mystery hidden within this greatness. Why is light so fast? Why is nothing allowed to outrun it? And why does the universe guard this limit so fiercely that even coming close causes time, mass, and energy to distort in wild, unimaginable ways? To understand why traveling light years at incredible speed is so difficult, we must step into the strange world of physics, where intuition fails, where reality bends, where time itself becomes negotiable. This is the realm where Albert Einstein left his mark, rewriting the rules of motion, speed, and existence. Imagine for a moment you are behind the controls of the fastest spacecraft imaginable, something far beyond NASA's rockets, beyond fusion engines, beyond any propulsion humans have conceived. Even with infinite fuel, infinite thrust, and no fear, you still face one fact. You can never reach or exceed the speed of light. Not because the universe punishes you, not because it is dangerous, simply because it is mathematically impossible. The speed of light, 299,792 kilometers per second, is more than a number. It is woven into the very structure of space-time, like the maximum tension a fabric can take before tearing. It is the speed at which information moves. It is the speed at which cause becomes effect. It is the speed at which the universe unfolds. To go faster than light is to ask for the impossible. Faster cause and effect, backwards time, instant communication across infinite space. These things violate the fundamental logic of reality, and so the universe draws a line and says, you may approach, but never cross. But what happens as you approach? Here the universe gets strange, very strange. When we talk about traveling light years, we imagine jumping from star to star, streaking across the void in a radiant blur. But traveling at such speed means entering a world where your mass increases, everything around you contracts, time slows down relative to everything else. Energy requirements explode beyond comprehension. It is as if space itself pushes back. Let's examine each of these cosmic barriers. 1. Mass becomes a problem, a big one. As your speed increases, your mass effectively increases as well. Not the mass you feel on a scale, the mass that resists acceleration. A spacecraft that weighs 100 tons at rest might weigh 200 tons at 80% light speed, 500 tons at 90% light speed, 1,000 tons at 95% light speed, 10,000 tons at 99.9% light speed. This is not metaphorical. The ship literally becomes heavier, not because it gains physical material, but because energy and mass become interchangeable at high speeds. To accelerate something infinitely heavy to infinite speed would require infinite energy. Humans do not have infinite energy. Thus, the universe protects its speed limit with incredible elegance. 2. Time slows down, but only for you. This is where relativity becomes beautiful and terrifying. The faster you go, the slower time passes for you compared to the outside world. Imagine you travel to a star 10 light-years away at 99.9999% the speed of light. To people on Earth, your journey takes almost exactly 10 years, but to you on the ship, maybe a few months, perhaps a few weeks, or even a few days depending on how close to light speed you are. You are not cheating the system. You are not teleporting. You are not bending the rules. You are simply experiencing time differently because you are moving so fast. This is not science fiction. This is measured, proven, and real. Astronauts aboard the ISS age milliseconds slower than we do. Fast-moving particles survive far longer than they should. GPS satellites must correct their clocks to account for relativistic time. Speed changes time, and light speed nearly stops it. This is both amazing and tragic. Because while you may feel like you are traveling for a few months, thousands of years might pass on Earth. You could leave home and return to a planet where everyone you know has vanished, where cities have risen and fallen, where humanity has changed beyond recognition. Traveling light years fast enough to reach other stars might mean becoming a ghost of time, a visitor from the past. 3. Space itself shrinks around you. This is the strangest effect of all. When you approach the speed of light, distances contract in the direction of travel. If a star is 10 light years away, but you travel at 99.999% of light speed, you may experience the distance as 1 light year, 1 month, 1 day, 1 hour, depending on how close to light speed you get. In your frame of reference, you truly travel less distance. The universe does not cheat. The distance remains 10 light years to everyone else. But your motion changes the geometry of space-time itself. This means one shocking thing. Interstellar travel at near light speed is possible for the traveler, not for the people watching from Earth, not for those left behind, not for society, but for the individuals aboard the ship. Yes, it becomes possible to cross the galaxy within a lifetime. The price? Relativity itself. If you travel far enough fast enough, you may return billions of years into Earth's future, long after humanity is gone, long after the sun dies, long after Earth becomes dust. You can outrun distance, but you cannot outrun time. Let's assume you want to reach 99% of the speed of light. The energy required is equivalent to the total energy of entire nations, the energy output of the sun if scaled up. More energy than humanity has produced in all of history. And that is just for one spaceship. Accelerating a 100-ton ship to near light speed requires quadrillions of joules, amounting to thousands of nuclear bombs. Decades of Earth's energy output, levels of power that today exist only in supernovae, neutron stars, and black holes. This is the true barrier, not imagination, not fear, not engineering, energy. The universe demands a price for speed, a price so large that humanity has barely begun to comprehend it. Perhaps, maybe not today, maybe not tomorrow, but humans have never accepted their limits for long. There are ideas, bold, strange, beautiful ideas that could someday carry us beyond the solar system. Fusion engines burning like miniature stars, antimatter propulsion, the most energy-dense fuel possible. Light sails pushed by lasers across light years, warp fields that compress space-time instead of speeding up the ship. None of these exist yet. Some may never exist. Some may demand physics we have not discovered. Some may require materials that do not yet exist or energies we cannot yet produce. But in every age of history, humans have been staring at the horizon saying, "Impossible," right before they achieved it. This is the most important part. The universe does not hide the stars behind walls or deny us greatness. The universe simply operates on rules, rules that shape reality, rules we are still learning to master. The speed of light is not a punishment. It is a boundary, a frontier. And human beings are creatures who cross frontiers. Even now, as our spacecraft drifts slowly through space, we are learning, improving, evolving. We are designing engines that burn hotter, run longer, push faster. We are studying the nature of energy, gravity, and space-time. We are discovering technologies that seemed impossible a century ago. Humanity may crawl today, but one day we will run. And after running, we will fly. And after flying, perhaps we will glide on the currents of space-time itself. The barrier of light is not the end. It is the beginning, the great challenge that defines our cosmic journey. Traveling light years at incredible speed is not just engineering. It is a battle against the structure of the universe. Mass increases, time slows to a crawl, space shrinks, energy demands explode, causality forbids surpassing light speed. And yet, none of these barriers say, "Do not try." They say, "Try harder." The cosmos is vast, indifferent, and relentless. But humans are stubborn, curious, and endlessly ambitious. We may never outrun light, but we will chase it. And in that chase, humanity will find its greatest adventure. Every discussion about light years and incredible speed often turns toward technology, engines, fuels, propulsion systems, or theoretical physics. Yet, as we push the boundaries of possibility, one question lingers. What would it feel like to actually travel at near light speed through space? It is easy to imagine stars streaking past, space bending into ribbons of color, or the thrill of moving faster than anyone has ever moved. But the reality, if we could ever get close to light speed, is far stranger, far more alien, and far more profound. Because at these velocities, the universe itself begins to behave differently, and human perception is challenged in ways that defy everyday experience. At near light speeds, almost every assumption about movement, time, and perception is upended. Consider this. On Earth, moving at 100 miles per hour feels fast. The wind rushes past your face, trees blur at the edges of vision, and acceleration presses you back into your seat. Now, imagine accelerating not to 100 miles per hour, not to thousands, but to 99.9999% of the speed of light. To anyone observing from Earth, your spacecraft is moving nearly instantaneously across interstellar distances. From your perspective, time inside the ship slows dramatically compared to Earth. Seconds might stretch into minutes, minutes into hours, and a single hour aboard the ship could equal years outside. This is time dilation, one of the strangest effects predicted by Einstein's theory of special relativity. Time dilation is not theoretical. Particles moving near light speed live longer. Atomic clocks flown in aircraft or satellites already show tiny but measurable differences compared to stationary clocks. At near light speed, this difference is magnified to extremes. For travelers, life continues at a seemingly normal pace. They sleep, eat, think, and dream. But when they glance at Earth, decades or centuries may have passed. Imagine leaving your home planet in 2100, journeying at near light speed to the nearest star, and returning in what feels like a single lifetime. You arrive back to find the Earth of 500 years later, an alien world, unrecognizable, and perhaps populated by generations that never knew you existed. Humanity's history becomes a living tapestry moving faster than your own experience. The psychological impact of this reality is staggering. Isolation, disconnection, and the sense of becoming untethered from the familiar flow of human time would challenge the mind. Space travel at incredible speed is not just a physical endeavor, it is a confrontation with the very nature of existence. Physics also radically alters what you see. At high velocities, light no longer behaves as we perceive it under normal conditions. One dramatic effect is the relativistic Doppler shift. This is similar to the way a siren sounds higher pitched as it approaches and lower as it recedes, but applied to light itself. Stars in front of the spacecraft appear bluer, their light compressed into higher frequencies. Stars behind appear redder, stretched into lower frequencies, perhaps beyond visible light entirely. Light from the sides distorts, creating strange arcs, curves, and warps. The effect is known as relativistic aberration. Stars appear to bunch toward the direction of travel, warping space into a tunnel-like vision. The universe seems to collapse forward, like looking through a kaleidoscope where reality itself has been bent and twisted. For travelers, this would be both beautiful and disorienting. The familiar night sky, constellations, recognizable stars, and even the Milky Way would vanish into an unfamiliar stretching field of color and light. Navigation becomes a challenge, not because of lack of technology, but because human perception struggles to interpret these extreme visual shifts, and that is just the light. Cosmic rays, high-energy particles that normally stream harmlessly through space, become increasingly energetic as you approach light speed. Shielding against them becomes a necessity. At near light speed, every tiny particle is now a bullet traveling with unimaginable force. Even a speck of dust could pulverize the hull of a spacecraft and threaten human life. Traveling fast is exhilarating, but it is also dangerous in ways we barely comprehend. Before even reaching near light speed, acceleration itself poses a challenge. Human bodies are fragile. We are not designed to endure thousands or millions of G-forces. Rockets must accelerate gradually. or specialized technology must mitigate the effects on passengers. Assume we have mastered these technologies: artificial gravity, inertial dampeners, or even futuristic propulsion that sidesteps ordinary acceleration. Even so, moving at near light speed is unlike anything experienced on Earth. Weightlessness persists, but time, mass, and space distort. The familiar world of physics, falling objects, inertia, motion, begins to behave differently. Inertia becomes a critical factor. Turning, stopping, or maneuvering at near light speed could require energy comparable to entire planetary outputs. Every action must be calculated with mathematical precision. Even minor miscalculations could have catastrophic consequences. In a universe where mistakes are fatal, the cognitive load alone, knowing that one error could spell annihilation, would weigh heavily on any crew.
10,
Speed also changes how you connect with the rest of humanity.
6,
If you are traveling to Proxima
4,
Centauri at near light
3,
speed,
2,
Earth messages take
1,
years to reach you. Even
and
if you could
booster
transmit
ignition,
instantly,
liftoff of
the
Space Shuttle
delay would
Discovery,
feel like
taking the
isolation.
space station to full power.
By the time a
for full
reply
science.
arrives, decades could have passed on Earth. This is temporal separation, an effect no previous explorers have ever faced. Communication becomes asynchronous on an unimaginable scale. Loved ones, governments, and even civilizations evolve while travelers remain nearly frozen in their personal timeframes. It is a loneliness unlike any other. Even surrounded by advanced AI, fellow crew members, or virtual environments, the separation from the home planet would challenge mental resilience. The human mind is tethered to social interaction and shared temporal experience. Near light speed travel fractures that bond. Travelers would need extraordinary mental preparation, not just for survival, but to retain a sense of identity and purpose. Traveling at near light speed is not just a matter of perception or time. It presents very real, physical dangers. 1. Collision with particles. Interstellar space, though mostly empty, contains dust and gas. At near light speed, even a single hydrogen atom strikes with the energy of a bullet. Micrometeoroids become lethal projectiles. Spacecraft require impenetrable shielding. 2. Cosmic radiation. High-energy photons and cosmic rays intensify, posing life-threatening exposure risks. Normal spacecraft shielding is insufficient. Travelers must develop entirely new protection systems. 3. Thermal management. At high velocities, friction from even rarefied interstellar gas can generate heat. Thermal control becomes a matter of life or death. 4. Energy supply. Sustaining life, navigation, propulsion, and shielding across decades or centuries requires energy far beyond any terrestrial capability. Renewable sources, nuclear fusion, or exotic matter may be required. Even with these obstacles solved, the psychological strain remains. Isolation, disorientation, and the near-complete break from earthbound time and experience would test the human spirit in ways no one today can fully imagine. Now imagine this scenario. You are traveling at 99.999% of light speed. For you, weeks may pass, but for the rest of humanity, decades or centuries elapse. The stars in front of you blur into ribbons of blue. Light from behind fades into red. Your own body feels normal, yet every particle outside behaves differently. Even the perception of your ship's structure warps due to relativistic effects. Human perception, evolved for earthbound speeds and timescales, struggles to comprehend this. Your sense of motion, distance, and causality is distorted. Seconds may feel like minutes. Minutes may feel like days. The line between past, present, and future begins to blur. Despite all these challenges, there is exhilaration. To move faster than any previous human, to cross a star system in hours, to witness the universe's warp and flow firsthand, it is beyond imagination. It is both terrifying and awe-inspiring, a confrontation with the vastness of space and the relativity of experience. At near light speeds, distances shrink in the traveler's frame, as we discussed. Interstellar journeys that would normally take centuries become feasible within a human lifetime. The dream of reaching another star, of crossing the Milky Way over many generations, becomes tantalizingly real. Proxima Centauri, 4.24 light-years away, could take just months or years from the traveler's perspective. Alpha Centauri, 4.37 light-years, equally reachable. Even the edge of our galaxy, 100,000 light-years distant, could be traversed over lifetimes if near-light speed were achievable. This transforms our place in the cosmos. From a tiny planet in a quiet corner of the Milky Way, humans could become voyagers, travelers, and observers of a galaxy that once seemed unreachable. Near light-speed travel is paradoxical. From Earth, you are moving faster than anyone has ever moved, traversing unimaginable distances. From your own perspective, life continues almost normally, a few months or years passing as centuries slip by elsewhere. This paradox challenges everything we consider human experience. Time is no longer universal. Distance is no longer absolute. Connection with Earth is fractured. It forces us to reconsider what it means to journey, to explore, and to exist. To travel at these speeds is to confront the very relativity of existence, to become both observer and participant in a universe where space, time, and motion are fluid. Traveling near light speed is not a simple extension of rocket travel. It is a journey into the strange physics of the universe, where time stretches and shrinks, space contracts, light and perception warp, energy demands are astronomical. Human psychology is tested beyond imagination. Yet, it also promises experiences that are awe-inspiring, transformative, and unprecedented. Witnessing the universe in motion, crossing light years in a single lifetime, experiencing time and space in ways no human has ever known. Near light speed travel is terrifying, beautiful, and almost unimaginable. It challenges our minds, our bodies, and our civilization. But it also shows what is possible when humanity refuses to accept the limits of earthly experience. It is a glimpse of what interstellar voyaging could truly be, a journey where we are tiny, yet capable of moving at the fastest speeds the universe allows, facing challenges that are cosmic in scale, and witnessing the universe in ways that will redefine what it means to be human. Humanity has always been a species defined by movement. From the first footsteps across continents to the ships that sailed oceans, from the hot air balloons that lifted into the skies to the rockets that carried us to the moon, we have pushed boundaries. And yet, light years remain an entirely different frontier. To travel at or near light speed, we cannot rely on conventional technology. Not chemical rockets, not ion drives, not even the fusion experiments that tantalize physicists today. We must imagine, design, and engineer engines that operate on cosmic scales, and the challenges are as immense as the distances themselves. All human spaceflight to date has relied on chemical propulsion. Fuel is burned, gas is expelled, and thrust is produced. The Saturn V rockets that carried Apollo astronauts to the moon burned millions of kilograms of fuel to overcome Earth's gravity. Yet even these enormous machines could not reach 0.01% of light speed. The problem is simple. Chemical energy is too weak. The energy contained in a kilogram of rocket fuel, though enormous by earthly standards, is a drop in the cosmic bucket. To accelerate a spacecraft to near light speed would require energy levels equivalent to entire nations' annual energy output, multiplied many times over. Rockets are fine for moving across planets or even to other planets in the solar system. They are hopeless for interstellar travel. Even nuclear propulsion, the next step, faces limitations. Fission or fusion engines offer far more energy per kilogram of fuel than chemical rockets. Fusion in particular, the process that powers stars, could theoretically accelerate spacecraft to several percent of light speed. Yet, achieving 99% light speed would still require technologies and energy densities that currently exist only in the hearts of stars. One of the most promising concepts for near light speed travel is antimatter propulsion. Antimatter is the mirror image of ordinary matter. When matter and antimatter collide, they annihilate, releasing energy in pure, unimaginable forms. A single gram of antimatter colliding with a gram of matter releases the energy equivalent of 42 kilotons of TNT, roughly the same as the Hiroshima bomb. Multiply that by kilograms or tons, and you begin to see why antimatter is considered a potential interstellar fuel. In theory, a spacecraft powered by antimatter could accelerate continuously, approaching light speed within months or years. The energy density is such that tiny amounts of fuel could produce massive acceleration. But there are enormous obstacles. 1. Production. Humans currently produce only nanograms of antimatter at enormous cost and with extreme difficulty. 2. Containment. Antimatter must be stored in perfect isolation. Any contact with matter triggers an annihilation that would destroy the spacecraft. 3. Safety. Even a tiny leak could obliterate everything aboard. Despite these challenges, antimatter represents a pathway to velocities approaching the cosmic speed limit. It is a fuel that matches the universe's own energy scales, a way to chase light itself without the prohibitive mass problems of chemical propulsion. Another fascinating method is light sails, a technology that does not carry fuel at all. Light has momentum, even though it has no mass. Photons exert pressure when they collide with a reflective surface. In space, a giant, ultra-thin sail could catch the light from a star, a laser, or even the sun itself, gradually accelerating a spacecraft to extreme velocities. Projects like Breakthrough Starshot are already exploring this idea. Tiny probes, equipped with reflective sails and propelled by powerful Earth-based lasers, could theoretically reach 20% of light speed, traveling to Alpha Centauri in just over 20 years. The advantages are clear: no onboard fuel, constant acceleration, and the ability to use energy directly from light itself. The limitations are equally clear. The sail must be incredibly light and durable. The laser must remain focused across millions of kilometers. Communication and control at such distances would be difficult. Acceleration is slow at first, taking months to reach significant speeds. Still, light sails represent a concept that bridges science fiction and reality, giving humanity a plausible path to the stars within the next century. Fusion propulsion offers another tantalizing possibility. By mimicking the processes at the heart of the Sun, a fusion engine could release enormous amounts of energy from relatively small amounts of fuel. Unlike chemical rockets, which expel tons of matter for small thrust, fusion engines could accelerate spacecraft continuously over years, approaching a fraction of light speed. There are proposals like Project Daedalus and Project Icarus, which envision massive fusion-powered spacecraft capable of reaching 12% of light speed, enough to cross light-year distances in decades. The advantages: continuous acceleration, high efficiency, and relative familiarity with physics. Fusion is understood in theory, if not yet perfected in practice. The challenges: containing a controlled fusion reaction in a spacecraft, managing waste heat, and engineering propulsion systems that can survive decades of operation in interstellar space. If conventional propulsion, chemical, nuclear, antimatter, or light sails, remains too slow for meaningful interstellar travel, the only alternative may lie in manipulating space itself. Theoretical concepts like the Alcubierre warp drive propose compressing space in front of a ship and expanding it behind, creating a bubble that moves faster than light relative to distant observers, while the ship inside remains stationary relative to the bubble. This concept does not break the cosmic speed limit because the ship itself is not moving locally. Space is moving. It's a loophole allowed by general relativity. The challenges are extraordinary, requires exotic matter with negative energy, something not yet observed. Energy requirements may rival the mass energy of entire planets. Stability, navigation, and shielding against cosmic debris are unsolved problems. Still, the warp drive embodies humanity's ultimate ambition, not just chasing light, but riding the fabric of space-time itself. Even if propulsion challenges are solved, interstellar travel demands solutions for life support, energy, and radiation shielding. Life support, closed-loop ecosystems, recycling oxygen, water, and nutrients for decades or centuries. Radiation shielding. Galactic cosmic rays become lethal at near-light speeds. Shields may require dense materials or electromagnetic fields. Psychological resilience, isolation, time dilation, and distance from Earth would challenge even the most mentally stable travelers. Communication. At light years of distance, messages take years to arrive, creating profound isolation from Earth-based civilization. The challenge of surviving light-speed travel is almost as great as the challenge of reaching light speed itself. Technology is only part of the story. To travel at incredible speed is to confront our place in the cosmos. Distances shrink, but time dilates. Observers on Earth age decades while travelers experience years. Stars blur, space distorts, and photons strike with lethal force. Yet humanity has a track record. We adapt, we invent, we dream. Every great leap, crossing oceans, flying through the skies, landing on the moon, was once impossible. Today, we are still crawling in comparison to the speed of light, but every step brings us closer to the day when a probe, a craft, or perhaps even a human being will journey through the stars at unimaginable speed. Near light speed travel requires technologies that stretch the imagination. Antimatter engines, energy-dense, lethal, and efficient. Light sails, harnessing photons for acceleration. Fusion propulsion, continuous star-like thrust. Warp drives, bending space itself. Each approach carries extreme challenges: energy, materials, shielding, and survival. Yet, the very fact that these ideas are theoretically possible underscores humanity's enduring drive to chase the impossible, to follow light, and to expand our reach beyond the confines of our solar system. Every civilization has looked up at the night sky and wondered what it would feel like to traverse the stars, to move beyond the Earth, to experience the universe as something other than distant points of light. Yet imagining near light speed travel is different from experiencing it, or at least imagining it as the universe would present it. The laws of physics, as described by Einstein, bend the familiar rules of time, space, and perception, turning the cosmos into a living, breathing, and sometimes terrifying spectacle. To grasp what this journey would be like, we must explore not just the technology that could carry us, but the sensory, psychological, and existential reality of moving at velocities approaching the speed of light. At normal speeds, stars appear as fixed points of light in the night sky. The Milky Way stretches in a gentle arc, constellations are recognizable, and planets move predictably. But as a spacecraft approaches light speed, everything changes. Relativistic effects begin to dominate perception. 1. Aberration of light. Stars appear to shift toward the direction of travel. The universe seems to collapse into a tunnel, as though you are moving through a cosmic funnel. Space is no longer isotropic. It is distorted and elongated toward the forward axis. 2. Relativistic Doppler effect. Light is compressed in front of the ship, shifting toward the blue end of the spectrum. Stars behind the craft redshift, potentially disappearing beyond visible light into infrared or radio frequencies. The familiar night sky is replaced by streams of color, warping as your velocity increases. 3. Intensity increase. Radiation from cosmic sources grows stronger as your velocity increases. Photons strike with higher energy, bathing the spacecraft in a glow that is both beautiful and hazardous. At extreme speeds, unshielded sensors would detect X-rays or gamma rays, instead of the gentle starlight familiar to human eyes. The result is a universe that looks like a tunnel of streaking light, compressing ahead, stretching behind, and swirling to the sides. It is as if the cosmos itself is accelerating alongside the traveler, a living painting of motion, color, and distortion. For human perception, this is both awe-inspiring and disorienting. Depth cues fail, familiar reference points vanish, and the mind struggles to interpret this new geometry. Astronauts would need extensive training, adaptive visual aids, and perhaps augmented reality to navigate such a warped environment. Space is silent, a vacuum devoid of air and sound. At near light speed, this silence is profound. The roar of engines, the hiss of life support, or the hum of electronics becomes the only audible reality. Yet silence itself is a companion to isolation. The universe moves past you at unimaginable speed, but it does not acknowledge your presence. Stars, cosmic dust, and radiation streak by, utterly indifferent to your existence. The psychological impact of this silent passage is profound. Immense speed does not equate to immersion in life. It is an encounter with cosmic indifference. Some theorists speculate that traveling at near light speed might induce a form of sensory adaptation, where the mind prioritizes certain visual inputs, suppresses disorienting ones, and becomes attuned to the constant flux of relativistic effects. The traveler's brain must reconcile motion, warped light, and time dilation in real time, a cognitive challenge unlike any other human experience. Arguably, the most profound effect of near light speed travel is time dilation. As velocity increases toward the cosmic speed limit, time aboard the spacecraft slows relative to Earth. Seconds for the traveler may correspond to minutes, hours, or even years outside the ship. This effect is not just theoretical. It has been measured in particle physics experiments and in the clocks aboard satellites. Imagine departing for Proxima Centauri at 99.999% of light speed. The journey, as measured from Earth, might take over 4 years. For the traveler, however, only a few months may pass. The universe outside ages rapidly, while the traveler experiences only a fraction of that time. This creates a profound temporal dislocation. Loved ones, civilizations, and planets age, change, and evolve far faster than the traveler perceives. Returning to Earth could feel like entering an alien world. Friends and family may have disappeared, cities may be unrecognizable, history may have advanced centuries beyond what the traveler remembers. Time dilation, while providing a means to traverse interstellar distances within a human lifetime, imposes an existential cost. A growing detachment from home and the flow of shared human experience. Moving fast is exhilarating, but space is filled with dangers that multiply at relativistic speeds. Even the emptiest regions of the galaxy contain dust, gas, and radiation. Interstellar particles, hydrogen atoms and microscopic dust grains, harmless at low speeds, become high-energy projectiles at near-light speed. A collision with even a tiny particle could release energy equivalent to a cannon shot, capable of puncturing hulls or destroying critical systems. Cosmic radiation, high-energy photons and cosmic rays intensify due to relativistic effects. Shielding must be engineered not only to protect from ordinary radiation, but also to absorb the amplified energy of these relativistic particles. Temperature extremes. At incredible velocities, even rarefied interstellar gas can produce heat from friction, and radiation levels can rise to dangerous levels. Thermal management becomes critical to prevent catastrophic overheating or exposure to lethal radiation. Surviving these hazards requires a combination of engineering, foresight, and vigilance. Humanity's ability to traverse light years depends as much on protection and adaptation as it does on propulsion and speed. Beyond physical hazards, near light speed travel imposes profound psychological challenges. Isolation. The traveler is separated from Earth by light years. Communication is delayed by years, creating a sense of solitude that is almost unimaginable. Sensory disorientation, visual distortions, time dilation, and cosmic phenomena may overwhelm perception. The brain must adapt to a world where ordinary spatial and temporal cues no longer apply. Temporal detachment. As decades or centuries pass outside, the traveler remains young. This dislocation can generate profound feelings of existential loneliness. the sense of living outside the normal flow of human history. Yet, there is also wonder. To witness the cosmos at such velocities is to see reality in ways no human has ever seen before. Stars streak, galaxies warp, and light bends around the ship. Time itself becomes malleable, allowing travelers to experience a universe that is, for everyone else, static and unyielding. Traveling near light speed requires not only protection and perception, but precise navigation. Stars are unreliable guides. Aberration distorts their apparent positions. What looks like a destination may shift dramatically as speed changes. Galactic currents, gravity from stars, black holes, and dark matter subtly alters trajectories. Even minor miscalculations can compound over light years. Autonomous systems. On long journeys, spacecraft must operate independently, capable of course corrections, collision avoidance, and environmental monitoring without real-time human input from Earth. Navigation becomes a blend of physics, engineering, and intuition, a cosmic ballet where every move must consider both the relativity of motion and the unforgiving nature of interstellar space. Despite its dangers, near light-speed travel offers experiences beyond imagination. Visual poetry, the stretching, bending, and color shifting of stars creates a universe that is both alien and mesmerizing. Temporal perspective. Watching time pass differently outside your vessel forces a deep reflection on the nature of existence. Cosmic scale. The universe unfolds in new ways. Distances, once unconceivable, are traversed within a human lifetime. Travelers become participants in a universe that was previously inaccessible, observing its mechanics directly rather than through telescopes or simulations.
CLS, go for main engine
It is the
start.
ultimate form of exploration,
6,
a
5,
human
4,
consciousness moving
3,
through space-time
2,
itself.
1.
Near light speed travel is
And
not just a matter of
booster
speed,
ignition liftoff of
it is a
Space Shuttle
transformation
Discovery,
of perception
taking the space
and
station to full
experience.
power for full
Stars
science.
and galaxies warp into tunnels of light. Time dilates, separating travelers from earthbound reality. Particles and radiation become existential hazards. Psychological resilience is as critical as engineering prowess. Navigation and survival demand extraordinary precision. The journey is both terrifying and awe-inspiring. Humanity, in chasing light, confronts its own smallness and simultaneously its potential for exploration. Traveling at near light speed is not just about moving faster than anyone has ever moved. It is about experiencing the universe in its raw, relativistic reality. A frontier where physics, perception, and human spirit converge. Every journey into the cosmos is ultimately a story of humans confronting the universe, not just with technology, but with their bodies, minds, and societies. Traveling at near light speed through space is more than a matter of physics. It is a test of endurance, psychology, and the very structures of civilization. If humanity is to venture to the stars, we must first understand what it means to survive, thrive, and remain human in a regime where time, space, and perception are fundamentally altered. Even the most advanced spacecraft cannot shield us from the physical realities of near light speed travel. The human body is adapted to Earth, gravity, atmospheric pressure, oxygen levels, and the cycles of day and night. Spaceflight, even in low Earth orbit, already imposes tremendous stresses: muscle atrophy, bone density loss, radiation exposure, and psychological strain. Multiply these by the duration and conditions of interstellar travel, and the challenges become extreme. 1. Microgravity and prolonged weightlessness. At near light speed, artificial gravity may be required. Without it, bones weaken, muscles atrophy, and the cardiovascular system deteriorates. Centrifugal habitats or advanced inertial dampeners might simulate gravity, but their engineering demands precision. A failure could leave the crew physically debilitated. 2. Radiation exposure. Cosmic rays and high-energy particles strike with unprecedented intensity. Ordinary spacecraft shielding is insufficient. To survive, humans would need thick, dense materials, magnetic shields, or plasma-based deflectors. The energy requirements for these systems alone rival that of entire cities. 3. Sensory overload and disorientation. Visual and auditory perception is altered at near light speed. Light aberration distorts stars, while cosmic radiation may create aurora-like flashes inside the spacecraft. The brain must constantly recalibrate its understanding of direction, motion, and space. Without proper adaptation, prolonged exposure could induce chronic vertigo, hallucinations, or cognitive decline. The reality is stark. Surviving near light-speed travel requires not just technological marvels, but radical adaptations to human physiology. Perhaps the most profound challenge is temporal displacement. At velocities approaching light speed, time aboard the spacecraft slows relative to Earth. A single year on the ship could correspond to decades or centuries back home. This introduces the paradox of being young while the universe ages without you. Loved ones age or die while travelers remain relatively unchanged. Civilizations evolve, languages shift, and cultures transform. Technological and societal progress on Earth could surpass the traveler's understanding. For astronauts, this creates a psychological burden. They are explorers, not only of space, but of time itself. Returning to Earth, if possible, would feel like entering a world of strangers, where history has marched far beyond their own lived experience. This temporal separation may redefine the human sense of identity. Travelers could feel disconnected not just from loved ones, but from the very continuity of human civilization. For journeys spanning decades or centuries, near light-speed travel may require generation ships, massive spacecraft designed to house multiple generations of humans, with entire ecosystems on board. A generation ship transforms spaceflight into a self-contained civilization. Reproduction and education. New generations are born, grow, and are trained to continue the journey. Knowledge must be preserved and adapted to life aboard the vessel. Societal structures, governance, law, culture, and social cohesion must function within the confined environment of a spacecraft. Isolation and confinement magnify social tensions. Resource management, food, water, and energy must be recycled in closed-loop systems. Any failure could threaten the entire population. Generation ships are both engineering and social experiments, testing humanity's ability to sustain life independently of Earth while maintaining continuity across centuries. The challenges are immense: mutinies, social collapse, genetic bottlenecks, and the psychological strain of being born into a universe of metal walls and artificial skies. Even outside generation ships, near light-speed travel imposes extraordinary psychological demands: isolation and confinement. Travelers are cut off from Earth, surrounded by a sterile environment with only AI companions, fellow crew members, or digital interfaces for interaction. Temporal dislocation. Time dilation alters perception of aging, mortality, and relationships. The mind must reconcile subjective experience with the rapid evolution of the universe outside. Cognitive stress, navigating relativistic effects, monitoring radiation, and interpreting warped visuals creates continuous cognitive pressure. Psychologists hypothesize that successful travelers must combine emotional stability, adaptability, and deep intrinsic motivation. AI companions, immersive virtual environments, and structured routines could mitigate some effects, but the human mind is never designed for the profound isolation of relativistic travel. The journey challenges not only physical survival, but the preservation of sanity and purpose. Communication is profoundly limited at near light speed. Even at 99.9% light speed, signals sent to Earth lag by years or decades. Relativistic effects distort timing, meaning that messages from Earth may arrive out of sync with travelers' own experience of time. Any attempt at real-time guidance or collaboration is fundamentally impossible. This communication lag forces near light-speed travelers into autonomous decision-making, often confronting dilemmas with no input from home. the burden of responsibility is enormous. One miscalculation could have irreversible consequences, and Earth-based assistance may never arrive in time. Beyond individual experience, near-light-speed travel transforms society itself. Inequality of time. Travelers age more slowly than their peers on Earth. They become temporal outliers, straddling multiple eras of human history. Cultural drift. Generations born aboard ships may develop distinct languages, customs, and identities. They become spacefaring civilizations in miniature, potentially disconnected from Earth entirely. Ethical dilemmas. Decisions made on long voyages may affect generations, raising questions about consent, governance, and responsibility for those born aboard spacecraft. Near-light-speed travel is not just a technological challenge, it is a civilizational experiment, testing our ability to extend human life, society, and culture into interstellar space. To survive and thrive, humans must combine technology, biology, and psychology. 1. Engineering, shielding against cosmic rays, micrometeoroids, and thermal stress. Propulsion systems capable of continuous acceleration without catastrophic failure. Life support systems that are closed-loop and resilient. 2. Biological adaptation, medical technologies, potential genetic enhancements, or artificial organ systems to counter the effects of weightlessness, radiation, and long-term isolation. 3. Psychological fortitude, training for prolonged isolation, cognitive stress, and temporal dislocation. Every civilization has been defined by its pioneers, the ones who ventured beyond known boundaries, the ones who asked, "What lies beyond? How far can we go?" Humanity has mapped continents, crossed oceans, and reached the moon. But the stars, the true frontier, lie far beyond the reach of conventional experience. Traveling at near-light speed is the ultimate test of ambition, endurance, and ingenuity. It is a challenge not only of technology, but of existential perspective, asking what it means to move through the cosmos and to stake a claim in a universe measured in light years. Physics imposes hard limits. According to Einstein's theory of relativity, nothing with mass can reach or exceed the speed of light. As a spacecraft accelerates, its relativistic mass increases, requiring ever more energy for additional acceleration. The closer it gets to light speed, the more energy is required, asymptotically approaching infinity. This has profound consequences. 1. Practical speed limits. Even the most advanced hypothetical engines, antimatter drives, fusion propulsion, or laser-pushed sails, may realistically achieve 99.9% of light speed at best. Beyond this, energy requirements become physically unattainable. 2. Time dilation benefits and costs. The faster you go, the more pronounced the time dilation effect. Journeys that take centuries from Earth's perspective may take only years for travelers. Yet this temporal compression also creates dislocation, as travelers return to a world that has aged far beyond their own experience. 3. Communication and observation limits. At near-light speeds, causality and light travel time dictate what can be seen, measured, or communicated. The universe ahead is compressed, blue-shifted, and potentially lethal due to high-energy photons. The universe behind stretches, redshifts, and recedes into near invisibility. Human perception and instruments must adapt to a universe that is relativistically transformed. The laws of physics do not bend for ambition. They are strict guides, setting boundaries for how far we can push. Yet these boundaries also define a roadmap for exploration, a framework within which humanity can plan, innovate, and dream. Even at near-light speed, the universe is vast. Distances are measured in light years, and stars that appear nearby are still many trillions of kilometers away. Nevertheless, there are destinations that could, in principle, be reached within a human lifetime, if travelers harness relativistic effects. 1. The nearest stars, Proxima Centauri, 424 light-years away, hosts at least one potentially habitable planet, Proxima b. Traveling at 99.9% of light speed, a probe could reach it in under 5 years ship time, while over 4 years pass on Earth. Alpha Centauri A and B, slightly further, become reachable within a few additional years. 1. Barnard's Star and Wolf 359. Other nearby red dwarfs, 5 to 8 light-years away, could host planets or resources. These stars would be among the first interstellar destinations for probes or crewed ships. 2. Exoplanets in the habitable zone. Surveys from Kepler, TESS, and ground-based observatories have revealed thousands of planets within 50 light-years. Near-light speed travel reduces these vast distances to manageable decades for human travelers under relativistic time dilation. 3. The Oort cloud and interstellar medium. Even before reaching another star, a spacecraft traversing the outer solar system and the Oort cloud would encounter environments untouched by human exploration. These icy bodies, comets, and interstellar dust offer both hazards and potential resources for long-duration missions. Planning a near-light-speed journey requires balancing distance, resource availability, hazards, and mission purpose. Not every star is a destination. Some may be waypoints, others scientific laboratories, and a few potential refuges for human civilization. Humanity's ambitions extend beyond observation to colonization and the creation of off-world societies. Near-light-speed travel transforms not just travel itself, but the structure of human civilization. Generation ships. For journeys spanning decades or centuries, communities aboard spacecraft become self-contained civilizations. They carry their own culture, social systems, and governance. Each generation must balance survival, innovation, and purpose, ensuring the continuation of life across centuries. Seeding new worlds. Arrival at a habitable exoplanet does not guarantee success. Settlers must contend with unknown environments, alien ecosystems, and potential hazards. Terraforming, ecological engineering, or artificial habitats may be necessary to sustain human life. Cultural evolution in isolation. Over generations, language, customs, and values may diverge from Earth-based norms. Travelers may develop spaceborne identities, becoming fundamentally different from their ancestors on Earth. Interstellar networks. Even at near-light speed, communications lag prevents real-time coordination with Earth. Interstellar colonies may need autonomous governance, independent economies, and self-sufficient technology. Civilization itself must evolve to operate at cosmic scales. Traveling at near-light speed is not merely a test of endurance, it is a confrontation with a universe of hazards. 1. Interstellar particles, hydrogen atoms, dust grains, and micrometeoroids strike at relativistic velocities, releasing energy that can damage hulls, instruments, and living quarters. Even sub-millimeter dust becomes a dangerous projectile. 2. Radiation, high-energy photons and cosmic rays intensify due to relativistic effects, requiring multi-layer shielding, magnetic fields, or plasma barriers. Exposure without protection would be fatal. 3. Navigation hazards. Stars, planets, black holes, and nebulae distort space. Minor miscalculations could compound over light years, requiring autonomous navigation systems capable of correcting trajectories instantly. 4. Psychological hazards. Isolation, temporal dislocation, and sensory distortion challenge mental resilience. Even well-prepared crews face the risk of depression, social conflict, or cognitive overload. Human survival depends not just on speed, but on engineering, foresight, and adaptability. Near-light speed travel transforms not just distance, but perception itself. The familiar constellations dissolve into streaks of light. Galaxies warp, colors shift, and time bends. Events that unfold slowly on Earth, planetary rotations, solar activity, may accelerate into fast-forward sequences for the traveler. Astronauts witness a universe in motion, a perspective impossible from Earth. Light years collapse into months or years, yet the scale of the cosmos remains humbling. The traveler is tiny, fragile, and yet profoundly connected to the fabric of space-time. If humanity can harness near-light speed travel, what lies at the end of the journey? 1. Scientific discovery. Direct observation of exoplanets, black holes, interstellar gas, and distant galaxies at close range. Relativistic travel allows experiments and measurements impossible from Earth. 2. Expansion of civilization. Humans could establish independent colonies across dozens of star systems, ensuring survival beyond the solar system. Each new settlement is a safeguard against extinction. 3. Philosophical and cultural evolution. Travelers confront cosmic time, scale, and solitude. The experience transforms perspective, priorities, and understanding of life itself. 4. Interstellar legacy. Even if Earth is lost or civilizations change, humanity leaves behind a network of explorers, colonies, and knowledge repositories. Proof that we dared to chase the light and reach for the stars. Ultimately, the destiny of near light speed exploration is both outward and inward. It is the journey to the stars and the journey to understand our place in the universe. Speed and distance matter less than the wisdom, resilience, and imagination humanity carries into the cosmos. Near light speed travel represents the culmination of human aspiration. Physics limits velocity, but within those limits, vast distances become accessible. The nearest stars and exoplanets offer destinations, while the void itself offers lessons in survival. Time dilation and relativistic effects challenge perception, society, and psychology. Generation ships and off-world colonies test the endurance of human civilization. Cosmic hazards, radiation, micrometeoroids, and spatial distortion demand advanced engineering and foresight. Travelers experience the universe in ways earthbound humans cannot, witnessing reality at relativistic extremes. The ultimate frontier is not simply distance, but the integration of human life, technology, and civilization into the cosmic scale.